Good, welcome. Thank you for the introduction. I'm very glad that we can give a small presentation on what Vintecc is doing and how we use artificial intelligence towards our mission, which is creating smarter machines. First of all, I would like to start with a small introduction on myself, but also on Vintecc. So my name is Mathijs Degryse, and I'm working at Vintecc as a business developer since about 1.5 years. And honestly, before entering Vintecc, I thought that artificial intelligence was like a buzzword. You saw on every trade show, you saw machine learning and you saw predictive maintenance, but once you talk to the persons, then it was not really implemented yet. And then afterwards, when I entered Vintecc, I saw that AI is in fact everywhere. AI is in almost every software which we are developing with the outcome to create smarter machines. So who is Vintecc? Well, we are a software company and we create software for smart and connected machines for the entire industry. So it's not that we focus on one type of industry, but what you will probably see is that in the next slides, that there is often a common use. I don't do this alone, so we are a team of about 27 people. I think by this summer it will be around 30 people. And we have 3 offices, which is the headquarters in Roeselare. And we also have 2 side offices, one in Leuven and one orange one, which is in the Netherlands in Delft. But then the challenges, well, before this meeting, it was called problems. We have a problem. I think the industry where we are in, and let's say an more old-fashioned industry, which is mechanically driven, there are some challenges. And one of those challenges is that the machines are powered by software. So software becomes the main component in a machine. The second problem which we are facing is that they need to be delivered in a shorter time to market. So technology is evolving very quick, fast. So you need to develop, or you need to be up to date by also developing on a shorter time to market. And thirdly, this all needs to be developed by engineers and managed by engineers. So while there are no engineers available, so this needs to be done with limited resources. And that's why we developed ready-to-use frameworks for digitalization to fasten up the development time. And we also deliver solutions for vision and robotic applications. So we develop custom applications on demand for our customers, where they don't need to hire engineers themselves. And who are our customers? They are machine manufacturers, system integrators, and production companies. Our mission is to create smarter machine, and is based on this vision, which is the future of machines is smart, virtual, connected, and artificial. And this is the last one. The last pillar is the topic of today. But first, smart is embedded software. Every machine has software inside. Of every machine, there will be a virtual copy, which is called a digital twin, a virtual copy of a real asset. And thirdly, you have the machines connected to each other, to the cloud. It will collect data, analyze the data, and so on. The last pillar is artificial, which looks now like a vertical pillar, but in fact it's a horizontal pillar, because artificial intelligence is in every other pillar into our organization. One of the parts of the introduction was that machines need to be managed in an efficient way, and machines have different variants. Machines have data available, have software versions available, have digital twins available. So you need to connect everything. So you have an edge and a cloud, and this needs to be connected. And this is what we call the enterprise framework for smart machines, because we want to enable Industry 4.0 to the real applications. So at the left side, you see the computer vision, robotics, custom applications, which are connected to the platform. And at the right side, there will be Industry 4.0, like data analytics, industrial IoT, lifelong learning, all these kind of things, which are enabled by our in-house developed technology engines like Dual to create digital twins in an easy way and capture a real-time data collection and analytics tool. This was, let's say, a lot of theory, but how do we do this in real life? So what we do, you see here an application which is built for Stow Robotics, which was in the past well known as a manufacturer of steel for the warehouses. And then they wanted to make automated warehouses, and therefore they needed an HEV, which is running into the warehouse. And we developed the software for it, but there was no hardware available yet. So what we did is we created a digital twin, so a virtual model, and we started to test the critical test scenarios on that virtual model. Like you see here now, you see the red lines. These are sensors to detect the distances and so on. It looks a little bit like a promotional video, but it isn't. It is real software running on the virtual prototype. So what do you get back out of the digital twin is virtually replicated software. And once it's tested, it goes into the field and we start to collect data out of it. So at every moment, we see the health status of every machine in the field. Whenever there is a problem, for example, the machine goes into a hold or in a stop, we will be alarmed. Or even there is predictive maintenance inside. If, for example, a motor gets too warm, I don't know what problem there is there, we will be alerted, and we will know, okay, now we need to force a maintenance. Another big advantage of Capture is that once you have that connection with the machine, you can also do remote updates of your software versions. So you can easily manage the software versions of your machines. Like we are in Belgium, you have a machine in Italy, this machine gets a new software, you can just push the button and it will be updated from a distance. We also, on top of this, we create an extra layer, which is the asset creation and management, which I will not go too much into detail. Here you see some trusted key machine builders. And what do all these companies have in common is that they are, I wouldn't say always market leader, but they are really top in their market. And they invest in R&D and innovation. And this is where we come in. We add innovation or technology into the machines. But now back to AI. I would like to start with some basics. What is AI? What is machine learning? And what is deep learning? Artificial intelligence is like the human brain, but then in a software way, which can reason, react, and adapt. AI is everywhere. I will show you examples later. Where we focus on is more machine learning and deep learning. Machine learning is that you start to add extra data really to learn stuff to the machine. Then you have deep learning, where you stop adding, well, you don't stop adding extra data, but it will automatically add data and the machine would learn itself. Like in machine learning, there is still some feature extraction by a human being, while in deep learning, there is not, where you will work with neural networks from big quantity of data. Some examples where AI is used, like in OCR to detect whether there is, how do you call it, a mole, I assume, to detect the moles and to check if they are good or bad. Another example is the self-driving car, where you need to detect human beings, or you need to do obstacle detection, or you need to read really what's on the road signs, if it's stop or there is no, you cannot turn to the left and so on. So this needs also to be implemented in an algorithm and in a very robust way, because it should work in every circumstances. This means when it's raining, this means when it's sunny, this means where there is a lot of dust or fog, it always needs to work. So that's why today the self-driving car, there are still some security reasons. But it can also be used to make some predictions of temperature, but also predictions on stock market and so on. And finally, AI is also on your smartphone. If you have a Google camera, you can just scan some text and you can automatically make the translation to the language which you want. So AI is everywhere. back to the basics. Our brain works with millions of neurons, and one neuron is what you see at the right side. You have some inputs here. You have here the central piece, which make the calculations, in fact, and the interpretation, and then of all those inputs, and then an output will go out to the rest of the brain. If you make this a mathematical way, where it's artificial, then you have an input, which can be like a figure or a bit. You have a weight, so you make a calculation, you multiply x with the weight, and then you have here the sum of all the different inputs, and you make calculations based on a function. And here there are some examples of functions at the right side, which are often used, and then the neuron will make the calculation and send the output to the rest of the brain. This is how one single neuron works. But if you have more complexity, you need to use multiple neurons, and this is why they call it also a neural network. I will not go too much into detail, but you have different layers. You have an input layer, which you saw before. You have hidden layers, which make the calculations. In this example, there is only one hidden layer, but there can be multiple hidden layers. And then you have also an output layer. But how do you really train and how do you learn the algorithm? You have different ways to do this. I will explain some, like supervised learning. Supervised learning is that the word itself tells you have the input, and we know the input. Someone tells the algorithm, this is the input, and this is what I would like to become. This is the output. So, and the algorithm will make sure that input gets to the output. So under supervision of the person which is developing it. Then you have unsupervised learning. And this is when you do clustering of data. And then you see here, for example, three kind of bullets. And the algorithm doesn't know what is what. And he will try to cluster what he sees as is similar. An example is Google. If you do Google search and you type in bird, he will search at websites which also has bird, while he doesn't really know what bird is, but he said, okay, they're here. In this case, there is 10 times the word bird, so probably this will be what he is looking for. Then you have reinforcement learning. This is often used in games where you have action, where you have, for example, if you do something well, you get a reward, or if you do something bad, you get punished, and it will start to learn. But also, like Spotify is working in this case, where it does personalization based on what you say, this is good, this is bad, and this is called reinforcement learning. He will make some assumptions based on your behavior. An easy example, we will get some inputs. The outputs we know, this is a cat, a dog, and a bird. We get an input, and the algorithm will tell, okay, this is a cat. Second, this is a dog. Thirdly, this is a bird. So the input layer detects, he will go into the deep neural network, which is trained. And at the end, which you see here, the algorithm will tell, okay, the biggest, say in English, the biggest comparison is in this case with the bird. So he compares with other pictures in the algorithm. He will detect, for example, that his how he stands or what he has, that he has feathers and so on. So he will probably say, okay, this is a bird. Looks easy, and it's everywhere, so it should be easy, but at the end, there are still some challenges. And what are these challenges is the data. You need labeled data because the algorithm needs to know what is what. So, for example, an example might be, which is Google probably using to label the data. All of us is doing this. If you have the CAPTCHA, it will ask you, okay, where do you see a stop sign? And we click, okay, label data, and gets into the rest of the neural network. But how can you get labeled data? You can do this again by simulation, where we often use synthetic data. I will give some examples later. You have semi-supervised learning, like you have labeled data, you have unlabeled data. Put this together, and there is an algorithm which will start to label the data. And you have transfer learning. An example of transfer learning could be that you have, for example, a teacher which knows everything, and you have a student which already knows something. He has his own inputs, and the teacher tells the expertise which he knows, and the kid makes the student makes the interpretation. So there's a transfer of the knowledge of the teacher and the inputs of the student, and together it will make transfer learning. A second part is also the computational complexity. When you have very complex networks, like let's say the self-driving car, the algorithms take some time, or you need some calculation time and calculation power to do this. And because you don't want that the self-driving car is driving against no matter what, because he didn't interpret it fast enough, of course. So that's why this is quite complex, and this is why they are building all around the world supercomputers, where we can really make some fast calculations also in the cloud, because there is also a limitation in hardware which runs on the edge. Okay. The third challenge is there are also attacks, and an attack might be, they call it adversarial attacks. Like here you see a picture of a panda, and there is about 60% confident that this is a panda. But if someone also adds extra noise to it, here the algorithm will say it's a gibbon with 99.3% of confidence. So you can mislead the AI algorithm by adding noise. Another example here is it's not only pictures. Here is another picture, a duck, and then the algorithm tells it's a horse, but it can also be done on voice recognition. Here you see it really looks very similar, but at the end here it says, how are you? And at the end, if you add some noise, it says, open the door. Another example here, if you use a glass, that facial recognition is not possible anymore. Or sometimes you see on at the side of the road that they stick something on the road sign, and suddenly the AI algorithm doesn't detect the stop road sign anymore. And how can you avoid this? By using generative adversarial network. To explain very easy, you have a training set, which is very good, which explains what is what, and then you have some random noise, and you put this together, and you create an algorithm which might say this is real, this is fake. So you make the algorithm stronger by adding extra noise. To get back to the synthetic data, this was an internal project where we started to use synthetic data. You have a kind of a connector. Here you see at the right side the connector inside the box. We made a 3D part out of it, and we started to make virtual pictures of that 3D components. And we based our algorithm only on synthetic data. In fact, this is the outcome. So here you see that we have already some good results based only with synthetic data. But at the end of the movie, you will also see that there are still some mistakes. You see here that there is another picture of a shirt which he detects as a box. So this is not good. So you need to train the algorithm based with synthetic data combined with real data. This is often how we do this. If you go to some use cases, because now it has been theoretically, but how is it now really implemented into real use cases? I would like to start with an example which you all know, potatoes. Here you see how they transfer potatoes from A to B. But potatoes which come out of the field, they harvest them, but there are also rocks inside. There are also earth inside. There is also leaves inside. So you really need to do the sorting out of it. This can be done manually by persons, but then it's not that efficient, and it's also very costly. So if you use deep learning and vision, you will have better results. And why do we use AI and deep learning in it? because you have a large variety in objects to detect. You have the potatoes, but you also have stones and other parts which shouldn't be in it, especially here in Flanders, because of World War I. There are a lot of metal pieces which you can still find back and which you want to detect before the potatoes go inside the warehouse. Another reason why you should use deep learning is that we don't have a consistent background. Sometimes it's black background, sometimes it's gray, sometimes it's rolling. So you need to learn an algorithm still to detect the potatoes in all the kind of circumstances. And how did we start with it? We started to use synthetic data. You see here at your left side a synthetic picture of the data. So you will probably recognize potatoes and you will think, oh, this doesn't really look like a potato. Yes, that's correct. That's exactly what we wanted to achieve. That even with not pictures which are not really clear, that the algorithm can be trained. At the side, you also see some different backgrounds to make the distinction, to add some extra noise to make it more robust. On the right side, or in the middle, you see a real picture, and at the right side, you see the results of the algorithm based only on synthetic data. How does this look like? What you see here is a movie on the synthetic data. What we do, we make different kind of picture out of it. The big advantage from using synthetic data is that we already know the dimensions of the potato. So it will be much more easier to label the data afterwards. So here you see a stone, here you see some potatoes. You can switch with colors because sometimes there is a potato with a lot of dirt, which is more a dark color, and sometimes you have potato with no dirt, and then it's more like brown color. What is then the result? Here at the top, you see the result of the detection of unknown things. Like here you see a plastic bag inside, and you see what is a potato and what is not a potato. And at the bottom, this is then next level, let's say, is you do the detection of the potatoes, but you can also already do some classification of the potato, and classification in kind of, okay, what kind of potatoes do we have? You have a percentage of potatoes with this size, with this size, and this size. So you can really analyze also the outcome of your potatoes, how many kilos and so on. So this data is very valuable to our customer. Another project which we did was rock recognition. I will not tell the end application, but at the left top you see a picture, and I think this looks very real, but this is a picture of synthetic data. And also at the top, at the bottom left, you also see a movie on how we create this kind of synthetic data. So we let the rocks drop and we make virtual pictures while doing this. At the right side, you see real pictures where you see the detections of the stones and also the size of the stones. So again, a very good use case where we use synthetic data and where the result is quite satisfactory. But are we there yet? No, we are not there yet. We need to add also real data, and we need to train before really implementing it in a real case. Another part which is already in the field at certain customers is from De Man. De Man is a machine builder which creates machines to harvest Brussels sprouts, and they also have an optical inspection system. So here you see the sprouts coming in, and we take a lot of pictures, and we created an algorithm to detect which sprouts are good and which sprouts are bad. So here you see, and it's really not at the right speed yet because it goes much faster, but you see the speed, how fast it's falling. So in a few milliseconds, the algorithm needs to detect this is a good sprout or this is a bad sprout, and he will kick out the bad sprouts. While in the past, this was done by human beings or by humans. You have a harvester and a farmer, and he needed to, they needed to do with a few persons really to detect which ones are bad and good. So a lot of work, and the performance was just not good enough. And for the man, this, by adding this intelligence to the machine, it gave them a big competitive advantage, because in the past they sold a few machines a year, and now they sell about 20 machines a year, and they have a better result than their competitors which were in front of them a few years ago. But this is all based on vision. You can also use artificial intelligence on data, but then you need, of course, you need data for this. And that's why we built Capture. And Capture is a platform which collects data out of the machines. And here you have the edge part. So it starts with collecting the data. We have, on edge, we already have some databases where you can do some base analytics on it. And you can decide whether you want to synchronize the data to the cloud or not. And in the cloud, we have a complete platform to do visualization, alerting, and reporting. But here, the analytics part, this is where I want to focus on. You have an analytics part here, but meanwhile, we also have an analytics part here. So how does this work? Is that you can create functions or workflows in the data. This is the platform, how it looks like. Here are some movies with an example. Go more into detail. You do an extract of the data. You have an extra step. You transform the data, and you load the data back to the machines. So this is artificial intelligence, which how we implement it onto machines where you can do predictive maintenance with, or you can predict the certain outcomes of your machines. Another way how to do AI is, which is called model predictive control. So you see here two components, which is like a plant, and here you have an NPC controller. Here is where the actual software runs, and here you get sensor data. Here is the controller, where we have an optimizer, the software itself, and we have a digital twin of the machine. So here we have the algorithm which starts to create a process control, and we test the control system on the virtual digital twin, dus on the virtual plant, and it will agree or disagree. And if once it's the best case, the best input will be sent back to the plant. If you can compare this with autonomous driving. Here you have a self-driving car. First test which you do is you have to take this corner. Okay, it will get to the wall, so this is not good. We try another one. We go a very wide angle. No, we drive too fast and we collapse here. And the third one is, this is the optimal one, and this is what we will send back to the plants. This is how we start to build a model. We test the model on the virtual plant. Virtual plant gives back the optimal model, and this is what we send back to the process. This is the way how we also do the prediction of temperature, for example, based on the history. This is the past, and the blue line is the actual value which is measured. And at the right, you see the orange part. This is the predicted outcome. So what you see here is that we can be quite accurate towards the prediction of the temperature. So for this, in this case, it can be used also to control your heating, for example, while it's now done reactively. It gets colder, so the heating will go up until a certain temperature and go down again once the temperature is achieved. Well, if you use the prediction, you can already proactively heat your house, and to actually see what's happening, and this will be more efficient than every time go up, down, up, down, up, down. Voilà, and then I think we can come to a conclusion. For me, the conclusion is that AI is everywhere in our daily lives. It is now, but it will be certainly in the future, because if you're at the right side, you're looking at a study, top strategic technology trends for 2022, but also for the future. And there are different words where artificial intelligence comes back. So this is AI is now, but also in the future. A second one is AI is a mean and is not the goal. As told, for us, the goal is to create smarter machines, and artificial intelligence is a way to get there. And it's not obligatory, or it's not a demand in a smart machine to use artificial intelligence. We created already tons of use cases where no artificial intelligence comes in. And third one is that labeled data is key, and the best way is to combine it also with real data, is to combine real data with synthetic data. I also put here some myths and facts, because there are a lot of myths based on AI. And this is something which I found on the internet, which I think which is very easy to understand what is AI and what is not AI. If you have questions, you can always contact me. You have my contact details, you can have my email address, but you can also link via LinkedIn. I invite you to do this. You just type my name in it and you will find me back.